Hi there, this is Under the Hood. I am Mr. Wright, helping you to ace the AWS Certified Solutions Architect Professional exam. If you're serious about leveling up your cloud skills, make sure to subscribe for more practice questions and expert tips. Let's get the party started. You joined a startup deploying sensors to track street noise and air quality in urban areas. The pilot phase involved 100 sensors, each uploading 1 kilobyte of data per minute to AWS. During this time, the database had 10 IOPS and stored 3 gigabytes of data per month. The current setup uses EC2 instances for ingestion and a 500 gigabytes PostgreSQL RDS database. The company now plans to scale to 100,000 sensors and store data for 2 years. Your task is to ensure the platform can handle this increase and leave room for future growth. Which setup will meet the scaling requirements? Read the question carefully and try to find the right answer. If you need more time, pause the video when the clock appears. Alright, let's start from selecting the key pieces of information from the question that you should pay attention to. First, the number of sensors increased from 100 to 100,000. This is a major scaling factor. You must ensure the solution can handle a 1000x increase in the number of sensors and the corresponding increase in data ingestion, processing, and storage. Next, the data upload rate, 1 kilobyte per minute per sensor. Understanding the data rate is crucial for calculating the total data ingestion and storage needs. 100,000 sensors uploading 1 kilobyte per minute will require the system to ingest and process a much larger volume of data compared to the pilot phase. The third important fact, current setup, 500 gigabytes PostgreSQL RDS database. You must evaluate whether the current database can scale to store and query significantly more data efficiently. As the sensor count grows, a larger, more performant, and scalable database solution may be required. Next, storing data for 2 years. The storage solution must account for the total amount of data accumulated over 2 years, which will be significantly larger than in the pilot. You'll need to consider long-term storage solutions, such as S3, for cost efficiency and scalability. The fifth one, leave room for future growth. This implies that the solution should not just meet the current scaling requirements, but also be designed for additional growth beyond 100,000 sensors. Flexibility and scalability are essential. And the last but not least, database had 10 IOPS and stored 3 gigabytes of data per month. While these numbers were fine for the pilot phase, you'll need to consider how IOPS and storage requirements will scale with the increase in sensor count. The read-write performance of the database will need to handle the new data load. Now let's go through the options we have. Option A. Add an SQS queue to the ingestion layer to buffer writes to RDS. Well, this could help manage the flow of data during peak times by buffering the data before it is written to the RDS database. However, the key issue here is scaling. With 100,000 sensors continuously uploading data, the current RDS setup will still struggle to handle such a large volume of writes and reads, even with buffering. RDS will hit storage and IOPS limits, and you might face performance bottlenecks. While SQS can help smooth out spikes, it doesn't solve the underlying storage and IOPS capacity issue in RDS. Let's look at the option D, keep the current architecture, but upgrade RDS to 3 terabyte storage and 10K provisioned IOPS. While upgrading storage and IOPS will increase the database's capacity, RDS will still struggle with scalability over time, especially with the anticipated growth. As data grows exponentially over 2 years, managing 100,000 sensors and handling that data flow will quickly surpass the limits of even an upgraded RDS. Conclusion: temporary solution but not scalable for the long term. Option C. Replace the RDS instance with a 6-node Redshift cluster with 96 terabytes of storage. Redshift is designed for large-scale data storage and analytics, but it is not optimized for high-velocity real-time data ingestion like you would get from 100,000 sensors. Redshift is better suited for querying and analyzing data, rather than ingesting and managing transactional data at scale in real time. This setup would likely struggle with ingesting 100,000 sensors data in real time. Conclusion: not ideal for the real-time data ingestion requirements. So we have only option B left. Let's have a closer look at it. Ingest data into a DynamoDB table, then move old data to a Redshift cluster. DynamoDB is highly scalable and handles large amounts of data ingestion, making it a good choice for real-time data collection. Redshift, on the other hand, is great for storing and analyzing historical data. By using DynamoDB for live data and Redshift for archiving older data, this setup separates the ingestion and storage layers, making it scalable and cost-effective. This solution also provides the ability to analyze older data efficiently without burdening the main ingestion database. Good choice for scalability, handling both real-time and historical data well. Final recommendation: option B stands out as the best solution. It separates real-time ingestion with DynamoDB, which is highly scalable, and stores older data in Redshift for analysis, providing a robust, scalable approach for handling both real-time and historical data. Good luck with your exam prep, and I'm wishing you all the best in passing.